Deep down, every oil well is in this constant search for balance. It's this incredible dance between the raw power of the reservoir and, well, the limits of all the equipment we use. So the big question is, how do engineers find that perfect balancing point? Well, that's what we're going to get into. Okay, so to really get a handle on how much oil a well can produce, you've got to think of it like a battle. Seriously, it's a fight between two opposing forces. On one side, you've got the massive pressure the reservoir can supply, just pushing everything out. And on the other side, you've got the resistance of the whole system pushing right back. So who wins this thing?
All right, so let's meet our two fighters. First up, you have the reservoir's push. This is the natural pressure the reservoir has to shove oil out of the rock and into the well. You can totally think of it as the engine of the whole operation. And fighting against it is the system's resistance. This is all the back pressure from the pipes, the valves, all the gear. It's basically the pressure you need just to get the oil moving. A well can only produce right where these two forces find their balance.
Now, to really wrap our heads around that system resistance, we've got to follow the oil on its pretty epic journey, right? I mean, from deep underground all the way to the processing facility. Every single step along this path adds a little bit more of that resistance. So, where does it start? Well, the journey kicks off in the reservoir's porous rock. From there, it flows into the main wellbore. And then it's got to travel thousands of feet straight up through the production tubing. Once it hits the surface, it zips through a flow line and finally, it reaches the separator. That's where the oil, gas, and water all get split apart. The key thing to remember here is that each of these stages is just one piece of a single, continuous system.
Okay, so what's really fascinating about this whole trip is this idea of pressure loss. The best way to think about it is like an energy cost or a tax. As the oil squeezes through the rock, climbs up that long pipe, and navigates around bends, it loses energy. It's just friction, right? This pileup of pressure loss is the total resistance that the reservoir has to fight against and overcome.
So, with all that pushing and resisting, how in the world do engineers figure out the exact point where the reservoir's push perfectly matches the system's resistance? Well, they use this really elegant method called nodal analysis. It's basically a way to solve this pressure puzzle on a graph and find the well's natural sweet spot.
Okay, first let's look at the pressure the reservoir can supply. This makes a curve that goes downwards. Now, I know that sounds a little backwards, but think about it. The faster you try to pull fluid out, the higher your flow rate, the more the pressure right around the wellbore drops. So yeah, the available push from the reservoir actually gets weaker the more you flow.
And now for the other side of the coin, the opposing force. This is the pressure you need just to push the fluid through all those pipes and all that equipment. And this curve, it goes up. The logic here is super simple. The more fluid you try to cram through a pipe, the more friction you get, and so the more pressure you're going to need to do it. The resistance gets stronger as the flow gets higher.
So here's the magic moment. When you plot those two opposing curves, the one going down and the one going up, on the very same graph, they're going to cross at one and only one point. And that intersection, that is the well's natural flow rate. It is the only place where the pressure the reservoir can supply exactly equals the pressure the system requires. The system literally can't flow at any other rate. That's its equilibrium.
Okay, so we've got our method, right? But here's a really interesting question. This whole production system is just one long continuous path. So what happens if we decide to do our analysis to place our node, our measurement point, at different spots along that path? Do we actually get a different answer depending on where we choose to look?
Well, the source material gives us a huge clue here. It says, and I'm quoting, "The choice of node depends on which system component is being evaluated." So choosing where to measure, it's not random. It's actually a strategic decision an engineer makes depending on what part of the system they really want to dig into.
Let's put this to the test with a real example from our source material. First up, we're going to place our node way down at the bottom of the well. This is the classic standard approach. What it does is it splits the problem perfectly in two. You've got everything happening inside the reservoir on one side versus everything happening in the pipes going all the way up to the surface on the other.
So we run the numbers. We plot what the reservoir can deliver to that point against what the tubing and all the surface gear require from that point. The curves cross and boom, the solution is a production rate of 900 barrels of oil per day. Okay, lock that number in your head, 900. All right, now let's completely shift our perspective. We're going to move our node all the way up to the wellhead, right there at the surface. This splits the problem in a totally different way. Now we're comparing what the reservoir and the vertical tubing can deliver to the surface against what the surface flow line needs to move it from there. Okay, so we run the new calculations from this new viewpoint, and what do we find? You guessed it. The intersection gives us the exact same flow rate, 900 barrels of oil per day.
And this just brilliantly drives home the core principle. It doesn't matter if you analyze from the bottom of the well, the top of the well, or even right at the final separator. The answer is always the same, because a physical system like this has one and only one balancing point. The math is just confirming the physics of the real world.
Okay, so this naturally leads us to the most important practical question of all. If you always get the same answer, then why would an engineer ever bother choosing different nodes, right? Why not just stick with the standard bottom hole method every single time?
And the answer is because choosing a node is an incredibly powerful diagnostic tool. By placing the node at a specific spot, you can isolate one part of the system to see how different changes might affect everything else. For instance, you want to see how the well will perform as reservoir pressure slowly drops over the years? You focus on the bottom hole. Or maybe you're thinking about installing a bigger, more expensive flow line on the surface. We place the node at the wellhead. That lets you change just that one variable and see exactly how it impacts the whole system's performance.
So here's the big takeaway. Nodal analysis isn't just some fancy calculator for predicting a well's flow rate today. Its real power is as a what-if machine. It lets engineers model all sorts of changes, diagnose bottlenecks, and really optimize the entire production system to squeeze out every last drop as efficiently as possible.
It's really just a method of breaking down a super complex problem by finding that one single point where what's available meets what's required. And it kind of makes you wonder, doesn't it? From economics to ecosystems, what other hidden balancing points could we find in all the complex systems around us if we just knew where to look?